These are the Chapter 32 problems. We went over them in class on the 11th. And I want to just make sure if you weren't here or you want additional explanations, you can do that. So problem 5, we're using the point source of the Biot-Savart formula, which is a little annoying. So it's vacuum permeability times charge times velocity times this r hat, which is essentially the component of the motion that is acting perpendicular. So notice that's a cross product, or 4 pi r squared, which is the surface area of a sphere. So since the direction of this here, when it's 1 centimeter to the right and 1 centimeter down from the point of interest, that's a 45-degree angle. So that cross product of r hat is just simply sine 45 degrees. Charge is a proton, so that's the charge on a proton or electron. The distance I had to get using Pythagorean theorem, if this is 1 centimeter and that's 1 centimeter, so that overall distance is 1.41 centimeters, which converts to 0.0141 meters. So I end up getting 1.15 times 10 to the negative 15th Tesla, and that would be into the page at this point. For problem 14, there's a few parts of this, so it's basically asking you to find the field strength and direction at points A, B, and C. A is 2 centimeters above the top wire, B is directly between the wires, C is 2 centimeters below the bottom wire. So the first thing is I want to find the field strength when a point of interest is 2 centimeters away and 6 centimeters away, because all these distances are going to be either 2 or 6 from a given wire. So use the Biot-Savart formula for a long wire, which is this. You get 1 times 10 to the negative 4th Tesla. If it's 6 centimeters away, it's dividing all the other same stuff except divided by 0.06, which is a third as much, so that's 3.33 times 10 to the negative 5th Tesla. So then at point A, the top wire would cause the field to come out of the board or the page, and the bottom wire would cause the field to go into the page, and it's weaker. So the net field at that point is 0.00067 Tesla out of the page. Ooh, I think I forgot to do this. That's annoying. So top wire here causes, and the bottom wire each 2 centimeters away, and based on the orientation, they each cause 1 times 10 to the negative 4th Tesla into the page. So the net is 2.0 times 10 to the 4th into the page. Here, the top wire, that amount into the page because it's further away, this amount out of the page. So the net is going to be the same as this. So I'm going to go ahead and type that in. V net, not newt, equals 0.00067 Tesla out of the page. Not sure why I forgot to do that, but I forgot to do that. So same thing. All right, moving along to 21 here, and this is why I think I forgot this. I didn't draw these arrows on. I think the arrows are going clockwise. So if the arrows are going clockwise around here, maybe I can draw maybe an arrow. Yeah, we'll see. Make it a black color. Sure. So basically these are going clockwise, then in is positive. So therefore I have 6 amps coming out, 2 amps going in. I need a net of 3 amps going in because positive flux is defined as into the page if the arrows are going around clockwise. And so if I need 3 amps going in, I've got a net 4 amps coming out. I need a total of I3 to be 7 amps into the page. For 33, 34, they're kind of similar. They're actually, they're not. 33 and I believe 36 or maybe? I don't know, 60. At 30, maybe it's not that similar. So 33 deals with balance forces. So you have a 2-gram wire. It's in a magnetic field, 10 centimeters across. It's asking you to find the strength and direction of the magnetic field. So the gravitational force would be down. So to balance that out, we need a magnetic force upward. So the magnetic force equals, this is supposed to be a G, sorry about that. So that BIL is the force on the magnetic force on the wire, mg is the gravitational force. The current going through the wire is 1.5 amps. 10 centimeters or 0.1 meters of length. Said it was 2 grams, so 0.002 kilograms times 9.8 newtons per kilogram. And I get a field strength of 0.131 Tesla. So in order to have a magnetic force up using my right-hand rule, I would have to have the permanent field, this field pointing out of the page. So that's using the right-hand rule. Here, find the magnitude and direction of the force. When I'm given this as the magnetic field, this is a 10 centimeter cross section. First I'd find the current, so 15 volts divided by 3 ohms, so that's 5 amps. And then that length is 10 centimeters, so I'll use the Fabel formula. 0.05 Tesla was the strength that's given because it was 50 millitesla, 5 amps, 0.1 meters, so that's 0.025 newtons. And the force, if I have a current going down, field into the page, again using right-hand rule, is going to the right. Number 35, didn't do. Number 36, we talked about this one in class. Again, I may have solved this a little differently than some of you, but essentially what I want to do is figure out the field strength at the top, middle, and bottom wires, and then use that in the Fabel formula. So to find the magnetic field strength at those points, I know that the other wires are either 2 centimeters away or these 2 wires are 4 centimeters away. So I use this version of the Biot-Savart law to figure out the field strength at 2 and 4 centimeters, which is 1 times 10 to the negative 4th Tesla or 5 times 10 to the negative 5th Tesla. So for the top wire, the net field is going to be, this is at the top wire, the middle wire will cause a field to be going into the page. The bottom wire will cause a field to be going out of the page, so I subtract those. So the net field is 5 times 10 to the negative 5th Tesla out of the page. Plug that into F equals B times I times L, and I get that as the force on that wire. Now, if I look at the direction of the current in the wire and the fact that the magnetic field is going into the page, then that lets me know that the force is upward using the right-hand rule. Here in the middle, each of the wires is actually causing the magnetic field to go the opposite direction. So one of them into the page, one out of the page here. So I have no net field at this point on this wire, and therefore no net force. The bottom wire is basically a symmetrical with the top wire. Here we have, there's a little bit oddness with that, but here we end up having a stronger field out of the page than into the page, because the middle wire is closer and that causes a field out of the page. The top wire causes a field into the page on this location at the bottom wire. So the net field is going out of the page 5 times 10 to the negative 5th Tesla. So that would give us 2.5 times 10 to the negative 4th newtons downward. So this one is using the formula for a solenoid. That actually, I believe, is on your formula sheet, so something to keep in mind. There's a couple of different versions of this. N is total turns divided by length. Lowercase n is already in turns per meter. So plug in all the numbers, I get 3,180 turns. So I don't think this is a reasonable number for an 8 centimeter long magnet. Problem 60, I think we looked at that in class. So this is one similar to, I think it was 33 with balanced forces. So essentially in this case, what you've got to recognize is you've got an electric force and a magnetic force. The electric force would act on this electron upward, so we need an equal magnetic force that would act downward. There's a few formulas for electric field strength, dV dx, or delta V over delta distance, so volts per meter, and that also is equal to newtons per coulomb. And I've done that proof before. If you'd like to see it again, let me know. So if I rearrange these, I can solve that the electric force is going to equal 3.2 times 10 to the negative 5th newtons, because my field strength is 20,000 volts per meter, or 20,000 newtons per coulomb, and the charge on a proton or electron is 1.6 times 10 to the negative 19th coulombs. So now, if I get this electric force, I know that also has to be the magnetic force, and that's going to equal the magnetic force on a point charge, Q times V times B. And it's really a cross product of QV cross B. So I'll put that force in, same charge on the electron, know the speed of the electron, and I figure out the magnetic field strength is 0.002 Tesla, and that's going to be into the page. Now just to think about it, if I know that E equals F over Q, F electric is E times Q, F magnetic is QVB, notice that Q is in each of those equations, so I could set them equal to each other, since these forces, the magnitudes of the forces are equal to each other, and the actual charge cancels out. So the magnetic field strength is equal to the electric field strength divided by the velocity of the moving charge. That was kind of quick, so you can slow me down if you want, but I want to make sure that it's quick enough so that people won't completely tune out. So hopefully that helps, and that'll work.